In this activity, we'll use the visible flow of water through tubes as an analogy to the invisible flow of charged particles through an electrical circuit. In both cases, we have a closed system with a mobile material. In the case of a water circuit, the mobile material is water. In the case of an electrical circuit, the mobile material is charged particles. There is a constant amount of material, water or charge, present, independent of how or where it moves in the circuit. Here in my circuit, in my water circuit, I have a water pump, which is a source of energy. It's analogous to a battery in an electrical circuit. The clear tubes are our wires. These two mesh tubes serve as our resistors. And I have a flow meter, which measures the rate of flow of water through the circuit. It's analogous to an ammeter in an electrical circuit. Let's see how the flow rate, or the current, changes at different points in the circuit. First, I'll put the flow meter before the short resistor. I have the flow meter connected just before the shorter resistor, so let's see how long it takes for 10 rotations of the flow meter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9.1 seconds. Now let's put the flow meter in between the two resistors and see how the current changes. So now I have the flow meter in between the two resistors. Let's see how much time it takes for 10 rotations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9.65 seconds. All right, now let's put the flow meter after the long resistor and see how the current has changed. I've placed the flow meter after the long resistor. Let's measure how long it takes for 10 rotations of the flow meter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9.73 seconds. So there's some error because I have a reaction time when I'm using my timer, and so our values aren't going to be exactly the same. But within our experimental uncertainty, we can see that the flow rate, or the current, it stays the same when resistors are connected in series. Now let's take a look at pressure and see how that changes in the circuit. Let's look at pressure difference across components of our water circuit. It's analogous to electric potential difference in an electrical circuit. We can measure pressure using these vertical tubes. The higher the water in the tube, the larger the pressure. So let's measure the difference in pressure across these two resistors. One of them is short and one of them is a longer resistor. So the height of the water in this tube relative to the height of the water in the reservoir gives you the pressure of the water in the tube relative to the pressure in the reservoir. The height of the water before the short resistor is 68 centimeters. The height of the water in between the two resistors is 50 centimeters. The height of the water after both resistors is 8 centimeters. Okay, so we're interested particularly in the difference in pressure across the two resistors. We found that the difference in pressure across the short resistor was 18 centimeters, whereas the difference in pressure across the long resistor was 42 centimeters, much bigger. So what that tells us is for a larger resistor, we get a larger difference in pressure. Or in an electrical circuit, for a larger resistor, we get a larger difference in electrical potential difference. And it's this potential difference that drives the flow of charged particles through a circuit. Okay, now we have the vertical tubes across the water pump. Let's measure the height of the water before and after the water pump. This tube is before the pump, and the water height is 0. And after the pump, the height of the water in the tube is 70 centimeters. So the difference in pressure, which again is proportional to the height of the water in the tubes, is 70. If you remember earlier, we found the difference in pressure of the short resistor was 18, and the difference in pressure across the long resistor is 42. That adds up to 60. And then the battery adds 70 units of pressure, we'll say. So if you go around the loop one time, the battery adds 70 units of pressure, and then the pressure drops across both resistors, and the total amount should be 0. In our measurements, it's not 0 because we have other sources of resistance in our circuit. These junctions cause resistance, and even these tubes provide a small amount of resistance. But in general, the sum of the pressure difference around the closed system that we have here is 0. And this is consistent with Kirchhoff's loop rule. The sum of electrical potential differences around a circuit is always 0. Now you're going to use some simulations to answer some questions about circuit behavior.